We now look at section 6.5 of chapter 6, and it's on roots of complex numbers. So for a real number a and a positive integer n, an nth root of a is a real number c such that c to the n will give us a. And if a is less than 0 and n is even, so if a is negative and n is even, then no real nth root of a exists. For instance, there is no real root c such that c squared is equal to minus 1. On the other hand, if n is odd, then a has exactly one nth root, and for a greater than 0 and n, when n is even, a has two nth roots. Now we're going to look at this notion in terms of complex numbers. So let z be a complex number and n a positive integer. An nth root of z is a complex number w such that w to the n is equal to z. So for example, if we take the example in 6.5.2 where we've got z equals to I, we then show that w, which is root 3 over 2 plus half I, is a cube root of z. How do we do that? Well, we'll start off by writing w in polar form, and it is equal to e to the pi over 6I, right? So if we find the r, we'll find out the r is 1, and then the principal argument is pi over 6. Now we apply de Moivre's theorem, that's theorem 6.3.9. We will have w to the power 3, because we are trying to satisfy that, right? W to the power 3 is equal to e to the 3 times pi over 6, which is pi over 2I, right? And if we then do the exponential of pi over 2I, we see that that is equal to I, and therefore w is a cube root of I, right? So that's our example there. Let's look at a theorem, and this is theorem 6.5.3. And what does it say? It says, consider the non-zero complex numbers z, which is r1 e to the theta 1I, and w, which is r2 e to the theta 2I. Then z is going to be equal to w if and only if r1 is equal to r2 and theta 1 is equal to theta 2 plus 2 pi k for some integer k. So this is equality of complex numbers in the form of in polar form, right? So suppose z is equal to w, then obviously the r1 is equal to r2. That one is obvious. And furthermore, if we take r cos theta 1 plus r sin theta 1I, we'll see that that is equal to z, which is equal to w, which is equal to r cos theta 2 plus r2 sin theta 2I, right? And so by definition 6.1.2, and the fact that r1 and r2 are both not equal to 0, we can see that cos theta 1 is equal to cos theta 2, sin theta 1 is equal to sin theta 2. So the first part is pretty obvious. And so therefore, if we take, so if this is equal, then we can take cos theta 1 minus theta 2. If we use our identities, we find out that that is cos theta 1 cos theta 2 plus sin theta 1 sin theta 2, which is just cos squared theta 1 plus sin squared theta 1, which is equal to 1. But if this is equal to 1, then it means that the angle in here has to be 2 pi k for some integer k, but this will only mean that theta 1 is equal to theta 2 plus 2 pi k for some integer k. And then so that is the first part of the theorem. And then the second part, where you assume that this is equal to that and that is equal to that, and then you show that z is equal to w, is left as an exercise, and that is exercise 6.5, number 6 in the textbook. So you can go and check it out. Right, let's look at the next theorem, 6.5.4. So let z be equal to r e to the theta I be a non-zero complex number with theta the principal argument. Now for every integer n, z has exactly n distinct roots, and they are given by wk to be equal to the nth root of r e to the theta plus 2 pi k over n I, where k ranges from 0 to n minus 1. So so this is a theorem that tells us all the roots of a given complex number, right? And we are even told that they are if for an integer n, we are going to have exactly n distinct roots, right? So we are going to look at this proof. The proof has 3 parts, and we are going to do one part, and then the rest will be left as an exercise. So the proof consists of 3 parts. First, we show that if w is an nth root of z, then w is equal to wk. So we are trying to say if 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 you get any root, it has to be one of these. That's the first part, right? Then the second part is to show that each w is an nth root of z. So now we are sort of doing the converse. If we look at this, then it has to be an nth root, right, of z. So the first part was to show that if you've got an nth, if it is an nth root, it has to look like this. And now the second part would be to show that if this is a complex number, then it is an nth root of z. And then the last part will be to show that all these ones are different. Then you would have shown that there's that z has exactly n distinct roots, right? So we are going to prove the first part only, and then the second part and the third parts are left as exercises, and that's exercise 6.5, number 7 in the textbook. So let's look at the first part. So suppose w is equal to which is equal to s times e to the power alpha I is an nth root with alpha between 0 and 2 pi, I think. Then by definition 6.5.1 and de Moivre's theorem, it means that s to the n e to the n alpha I is equal to wn, which is equal to z. So we want to show that if this is the case, then it has to look like one of these, right? Now by theorem 6.5.3, s to the n has to be equal to r, right? And n alpha has to be equal to alpha plus 2 pi k for some integer k. So therefore s will be the nth root of r, and theta will be equal to, so if we take the n on that side, we get that alpha is equal to that. And since alpha is between 0 and 2 pi, then it means that the angle theta plus 2 pi k will also be less than 2n pi, right? And that means that if we subtract theta from both sides, we get minus theta there, 2 pi k, is less than or equal to 2n pi minus theta. And then if we look at the principal argument, so we know that theta is between minus pi and pi. Then what it means is minus pi is less than 2 pi k, which is less than 2n pi plus pi. Right, so what it means is minus half is less than k is less than n plus half. Right, so if we divide by 2 pi, we get that. Right, so since k and n are integers, it follows that between k lies between 0 and n. And what does that mean? That means w is equal to wk for some k between 0 and n minus 1. This is coming from this fact. Or w can be written as the nth root of r e to the theta plus 2n pi over ni, where so yes, so we've got these two cases. The first case is this is between 0 and n minus 1, the k, or it will be the nth one. So we are going to look at the nth one and see that that nth one is just the first one, w naught. Now, but by theorem 6.5.3, we know that this, which is that, is equal to, so if we rewrite this and divide by n, we get that plus 2 pi I. And this is supposed to be, well, the whole angle here is supposed to be multiplied by I. And then we know that 2 pi, we can remove the 2 pi. It doesn't matter in this case, so therefore we are left with that. But that is just w naught. If we look at w naught, that will be the way it looks like. So in other words, this case is already covered here, and so therefore w will be equal to wk for some k which is between 0 and n minus 1. Right, so that was the first part of the proof, and then as we mentioned, the rest of the proof is given as an exercise. Right, so now we want to look at some examples. So we've got a 6.5.5, and it says we find the fourth roots of z, where z is given by 2 root 2 minus 2 root 2i in standard form. So we want to find the fourth roots and then write them in standard form. So in polar form, to write this one, we find the r and then the theta, and then we find out that we can write z is equal to 4 e to the minus 4 pi minus pi over 4i. And therefore, applying 6.5.4, the fourth roots of z are going to be, and then we put the formula, root 2 is equal to all that. And in particular, if we put k to be equal to 0, then we find the first one. So it's a matter of substitution and then a bit of approximation there. And then if we do w1, we put 1 in there, and then we find something like that, and so forth. Right, so that is the idea. So you can so it's easy to follow how you get these values. And you can also look at 6.5.6 in the textbook. You can go and look at that. And so we've got a special case that we ought to talk about. And so a particularly interesting situation arises when z is equal to 1. And according to theorem 6.5.4, for each integer n, there are n distinct nth roots of z which is equal to 1. And then we call those roots of unity. So if z is equal to 1, we can find what we call the roots of unity. So in polar form, 1 is equal to e, so it will be 1 times e to the 0I. And hence by theorem 6.5.4, the nth roots of 1 are given by wk will be equal to e to the 2k pi over n, where k ranges from 0 to n minus 1. Now let us make a few observations regarding the nth roots wk of 1. So for each k between 0 and n minus 1, we have that the modulus of wk is equal to 1, right? Therefore, all the nth roots of unity lie on the circle with radius 1 and 0. Because their modulus is 1, we'll see with an illustration of a diagram of the argand plane that all the roots of unity will lie on the circle with radius 1 and center 0. Now the first nth root, which will be w naught, will be equal to 1, right? And if n is even, then w of n minus 2 of n over 2, so if you do the calculation here, you see that it is just equal to pi I, which is equal to minus 1. So therefore the real nth roots of 1 are complex nth roots of unity, right? And then so moving from wk to wk plus 1 along the circle, the argument increases. So this is the argument, the angle increases by 2 pi over n, from 2k pi over n to 2k plus 1 pi over n. And therefore the roots of unity are evenly distributed along that circle. The modulus of z is equal to 1. As an illustration of the general observations 1, 2, and 3, we can calculate the cube roots of 1 and represent them graphically on the argand plane. So we have the first one, we say that it's equal to 1. And now because n is odd, we don't have minus 1 as a root. But if n was an even number, say 4, then we will know that we have got a root at 1 and we have got a root at minus 1. And then we start moving with the argument increasing evenly, right? They will be evenly distributed. So because there are 3 and we have got 1 there, if you distribute them evenly, you'll see that that will be the angle there. So these angles will be the same, will have the same value. And so that will be e 2 pi over 3I, and if you write it in standard form, we get that, and then that one in standard form, we get that. So we get all the 3 roots that we have. So that is that. And as an application of de Moivre's theorem, we have found an explicit formula for the nth roots of a complex number, right? And a real number has no real nth roots, exactly 1 nth root, or exactly 2 real nth roots. And a complex number has exactly n nth roots. So we are comparing a real number and a complex number. So we'll see that for a real number, we have got 3 cases. We don't have any real nth roots, or we have got 1 real nth root, or exactly 2 nth roots. So that is the case for real numbers. But in the case for complex numbers, we are going to have exactly n complex nth roots. So what we are saying is the equation z to the 6, for example, which is equal to minus 1, is going to have no real solutions, but it has exactly 6. So whatever the power here will be exactly the number of distinct complex roots that we get. So that's what it's saying. So in actual fact, this is a special case of a theorem that is going to be discussed in the next chapter, which is the fundamental theorem of algebra. So that is that for section 6.5. Thank you.